Okay, so now we have Michael Porter, who is going to tell us about modern implementations, the social influence, in point processes.
Yeah, okay, thank you. Right, so there's a lot of processes, both physical and social, that exhibit clustering. And by clustering, we can refer to clusters, like what we've learned about so far, groups of data points that are similar to each other. We can also talk about clustering in the sense that when an observation occurs, let's say in time, that there can often be more than one observation occurring at each time. There's a dependent structure where the occurrence of event seems to come in pairs or triplets or more than one. You see this with earthquakes. So when an earthquake occurs, what are you concerned about coming next? An aftershock, right? And then sometimes aftershocks can cause further aftershocks and so forth. You also see this type of pattern in a similar sense with crime and conflict, terrorism activity. And you'll tend to see when a terrorist attack occurs that usually other ones can occur close by. There's a lot of reasons for this. I won't get into all of them. But I'm focused on trying to model predictive models for capturing the patterns in these types of contagious or another term that gets used is self-excited point process models. If you look at the figure on your right, you'll see the x-axis is time, year, and the y-axis, is the star rating for reviews of a restaurant. So in the U.S., there's a Yelp website that allows people to rate their restaurants or services and so forth. And so that top row is 5-star reviews, 4-star reviews, and so forth. And you see some interesting patterns. First, you can see that when events occur, there tends to be maybe more than one as you kind of have some of these events. So there's clustering there. You also see patterns over time where there's no poor reviews, and then we get maybe an excess of poor reviews and so forth. You also see these models in contagious disease. So if you happen to get sick, you can spread that to others that you come in contact with. Okay, so what's a point process? It's just, so I'm going to be a little loose with descriptions here, so bear with me a little bit. But a point process is a stochastic model governing the occurrence of events. I'm going to be always in the time domain, but events can also have other characteristics or marks. N sub t is a counting process. And I'll just refer to the notation. This is also very loose here. But H of t is just the event history. It's going to use to contain all the information in the stochastic process up to time t. Okay, so everything that we can learn about the history of the pattern of event sequence up to time t. This is an illustration of a point process, just a realization, a point pattern. So at a certain point of time, an event occurs, our counting process increases by 1. When the next event occurs, it increases by 1, and so forth. So this looks like a cumulative distribution function, and it's very similar, and there's a lot of properties that you can look at that have some correspondence, except you're not bound by 1. This is just going to go up to the number of events that you occur over your observation period. So a conditional intensity function, lambda t, is the event rate at time t. And I want to explicitly focus on conditioning on the history of the point pattern, because for the processes where there's contagion or self-exciting event, the history of the event process is going to influence the intensity. And so the idea of a self-exciting process is that when an event occurs, it's going to boost the intensity for a future time period. So here's an example of 2 point patterns. The one on the left is from process 1. The one on the right is from process 2. There's some similarities between them. So if you look, there's kind of a cluster of events early on, maybe another cluster later on. You see something kind of similar between both processes. But another difference between them is on process 1, even though there's a cluster of events, you don't really see clustering. So there's points in time where there's an event, but then there doesn't seem to be many events happening together in pairs or triplets. However, on the right-hand side, you don't see that. You see evidence of clustering, where an event occurs, they usually don't occur by themselves. There's several events. And to generate these two processes, and the way that I try to distinguish between the type of pattern that you can see in the realization of a point process is to explain clustering or try to examine clustering by two sources. One is exogenous forces, exogenous terms. So these are, if you're looking at, let's take the earthquake example, spatially earthquakes are going to happen near fault lines. And so there's an exogenous predictor variable, if you will, would be location of fault lines. Okay, so that's going to drive where earthquakes are going to occur. And then endogenous features are those that are, again, driven by the occurrence of the point pattern itself. So this would be trying to model earthquake risk due to aftershocks. Right? So due to a main earthquake, there's going to be an increased risk of a subsequent earthquake. Are there earthquakes in this area? Is this,
Not really.
Yeah.
In the mountains part.
Okay, good. So we don't have to experience this live, but if there was an earthquake, you don't want to rush back inside right away, right? For a number of reasons, but aftershock. Okay, so how did we get these two processes? So the tick marks here are the event realization for both the two processes, and what we're looking at is the event rate. What I use to generate these points comes from two different models. Sorry, this light blue didn't come out very well, but process one was generated by a heterogeneous Poisson process. So the intensity just has these two modes to it, and I can write the intensity just as a function of this background process, is the term that I'm going to use, which is just captured by this shape. The pattern on the right, which actually had some similar appearance, was driven by a Hawkes process, and I'll define this in just a second. But essentially, it's a model that represents the intensity at time t as a function of a baseline process or background process. In this case, this is a constant. And then you have this term over here in orange, which is a sum over past event times. So the intensity at time t is going to be a function of the difference in time between lambda t, between the t that we're estimating the intensity at, and past event tj. Okay, and so this whole term, I'll call it a boost term. Sometimes it's called shot noise, if you've seen that expression. And so what's a Hawkes process? So a Hawkes process specifies a conditional intensity that's comprised of a background process. This is a function over time. And then, again, this boost term. Okay. I think actually, so this Hawkes refers to Alan Hawkes, who kind of came up with this model. And specifically, Hawkes defined a constant background process and an exponential form for this decay. But I'm going to be a little more general, I think. So we'll be a little looser here and we'll allow this to be non-constant in time, and we can have some non-exponential terms for the boost component. Okay, so the background process is going to be non-negative. H is going to be this self-exciting or contagious term. And H should have the property that it's non-negative, that it has positive support, and oftentimes here, I'll mention something. We'll come back to this a bit, but the intensity is the event rate. If a previous event can generate more than one expected future events, then our process is going to explode. So as time goes on, we'll essentially get increasing events. So normally, when we go to estimate these models, we may want to have a restriction that we prevent H from being too large. Okay, so let's look at this, some common forms for the clustering term or the contagion term. So this is H. U is the time between current time and a past event. And so an exponential decay for H is such that an event occurs, so we have an earthquake occurs, or someone makes a rating on the Yelp website. There's an increase in risk of a future event. The intensity is going to increase initially. And then in an exponential model, the decay is going to be exponential. So as we increase in time units away from the event, the increase in intensity is going to start to decay as well. Over on the right-hand side is just the whole boost term. So these little ticks correspond to events that have occurred. And notice an event occurs, you get an increase in intensity, it starts to decay exponentially according to this pattern. Another event occurs, it boosts up. Another event occurs, and you kind of get this sawtooth pattern. The little dotted lines here just refer to me putting this function on top of each event. Okay. Does this look familiar to anything that you might have come across? Yeah.
Circuits often, circuit analysis often has this kind of short noise.
Yeah. But as far as right, this is something a commonplace where you see these. But if I think about these, if I call these things kernels, right, and I put a kernel down on top of each point, does that sound like anything you've come across? Yeah.
Density estimation.
Yeah, like kernel density estimation, if you've heard that term, right? A non-parametric way to estimate densities is you specify kind of a shape, a kernel, and you put it down, usually centered at each event. In this case, you can actually think about these types of processes as a density estimation. In this case, it's intensity, so it's going to be a density multiplied by an overall rate term. But this is a one-sided kernel, so a predictive one-sided kernel. And so this type of structure is actually the way that actually often has good predictive properties as well, even in this non-parametric kind of setting. Okay, so moving away from just a single parameter exponential form, we can take a two-parameter parametric model, like a gamma. Right? This is just a gamma PDF. But here we see that this type of structure can create a pattern where an event occurs, and then there's a bit of a lag before you get the increase in intensity. Okay, so think about, we'll see contagious diseases is probably a good one. You get exposed to a disease, and there's an incubation period before you become contagious. So the likelihood that you cause additional infections is going to be maybe a function of how likely your incubation period is before you become contagious. This is the peak of your contagion, and then as time goes on, you start to recover, and this is kind of the probability that you recover and are non-contagious at a certain point in time. And so these types of models, as you can assume, can also be used to model, so that these point process models, self-exciting models, have been used recently to try to understand the COVID spread and flu and sort of thing. And then now the gamma shot noise has kind of a similar pattern here, but now because we have a period of delay before the increase in risk, it looks a little different. This also can be common in understanding flow of information. So somebody produces a news event, something newsworthy occurs, there's a little bit of time before it gets put on social media, and then there's a little bit of time before people see it, and then spread that way. So we've used these types of models that we're going to refer to try to understand the spread of fake news, for example, on social media activity, and try to understand what's driving the fake news spread in the sense that we may be able to control it or prevent it if we understand the components of it. Okay, so we have this expression again that you'll see, a background plus a boost. And if we think about Poisson processes, there's a superposition process that indicates that if you have independent events and we want to model the overall or series of processes, and we want to model the overall event rate, we can just add up the sum of the intensities from the different processes. And so we can kind of look at this as saying that our events can be attributed to different components. So when we have an event occur, an earthquake, we could say that, try to attribute that earthquake as coming from the background process, would be like the main earthquake. And then we could also try to attribute additional earthquakes to the aftershock component. Okay, and this is actually something that seismologists try to do. They want to create earthquake catalogs, and they want to only use the main earthquake, which isn't always easy to identify. And so some of the things that we'll talk about are used now to kind of identify what the main earthquakes are. Okay, so if you're familiar with branching theory, for example, you know that events can come from An immigrant process is sometimes referred to as the background process, and then offspring. So each event that occurs can generate additional events, and we can capture those with the boost term. Okay, so here's an illustration. So what I have is this is what's observed. This the time of events. And here the number, you can ignore the number. This is an example where it was the star rating. So a 5-star review, 4-star review, we can think about these in general events. Right? What we don't get to see, but what's going to be useful in a couple different places. One, to estimate model parameters and also just understanding what's driving the process of individual events, is to understand if this event came from the background or from kind of generated by one of the previous events. Right, so here we have that the first 3 events were from the background process, but then this event produced an aftershock. It led to the generation of a subsequent event. Okay, and a property here that we have with this form of Hawkes model is that an event occurs, any type of event can generate offspring, I guess primarily at the same rate, with the same function. So here this event actually triggered 2 offspring, and then this offspring generated another one, right? So you get these kind of families of events that were all initiated from event 1. Okay, so if you're familiar with maybe Twitter or X, I know it's called, that's kind of a strange way to say it, but someone makes a post, right? I like, it's always fun to look at Donald Trump examples here. I don't think he posts on Twitter anymore, but he would make a post and then it gets a very large reaction, right? And so this kind of drove behavior on social media activity, and then someone made a post that someone else responds to and you get these long chains, right? And so one thing that we'll look at is the intensity of the parent process. So an event occurs, basically this kicks off another potential point process with intensity like this. Okay, so the jth event initiates another point process, and this is the intensity of the point process. It's going to be a function of at least the time between current time and event time j, but also you'll see in some examples where there's some other attributes that we can bring in to try to capture that intensity function. And then we also have we can look at the conditional probability that event I was triggered by past event j. Okay, so it's just looking at the intensity of the parent process divided by the overall intensity at time I, at the time that ti occurred. Okay, so this means that we can try to understand was in an event, so this is event I, we want to try to understand what's the probability that event I was generated from here, what's the probability that event I came from the background process, and so forth. Right? So if we're thinking about the spread of fake news, it's going to be important to understand was fake news spread because there was someone very influential spreading it. Right? So it may be that we want to capture, have an understanding of was fake news event I attributable to somebody else with certain characteristics being able to post that, someone that may be considered trustworthy. So just as far as trying to put some help modeling is to parameterize this parent process, just breaking it into 2 components. The first, alpha j, is the branching ratio, and then g of j is going to be a PDF. Okay, have the properties of a probability density function, non-zero, raised to 1, and so forth. And by doing this with the decay term over here, the g, that means that our branching ratio, or alpha, is the expected number of first-generation offspring from event j. Okay, and what we're going to do is try to model alpha j, and we're going to try to model the decay term, and by breaking these 2 apart, it's going to end up being a little easier to estimate the parameters for the component set. All right, so we have a form of the Hawkes intensity background process parameterized by theta b, a boost term parameterized by theta c. So those are 2 parameters. The log likelihood, if we're observing the point pattern from time 0 to t, okay, is going to look like this. The first term just looks very much like what you would get if you had a density estimation problem. All right, and so instead of having a density here, we have an intensity. And then we just have the term over here that's accounting for the overall intensity, the overall event rate at time t. And so now by plugging this in over here, what we have is a sum of logs, and in the log is sums. Right? You probably saw an expression like this on the first day, right? In mixture modeling, right? Because it's really the same thing. It would be more convenient for us to estimate everything if the sum was outside the log, right? And so we have essentially a mixture model representation there. Okay? It's just a mixture of plus-ons. And so, of course, if we knew this branching structure, meaning that if we knew that event I was caused by event J, and we had that information, I'll use the same terms that you probably saw Z as like the latent variables that's unknown. Right? If we know that if that's a 1, if I was triggered by J, or 0 otherwise, then we can break the likelihood down into 2 independent components, and we can estimate the parameters for the background process by itself, and we can estimate parameters from the boost term by itself, and this is actually a sum of sums, so you can further kind of write this out as a set of terms. And so this is kind of the missing data framework, and so we can estimate everything with EM in a pretty nice structured way. Okay, so just briefly, since I think you're familiar with this concept at this point. So from the EM approach, we're going to have the 2 steps. The E step is going to be estimating the probability of the branching structure. So again, the probability that I was generated by passive J looks like this. PII is the notation just to say the probability that event I came from the background process. And that's the background term at time ti over the overall density. And then we can update the estimate our model parameters for each component using these 2 likelihood equations. Okay, any questions about that? I know that was kind of brief and not overly detailed, but I just wanted to make that connection to mixture models. Okay, so what I'm going to do now is just go through 3 applications of how I've used these models in some different ways. The first one is using models like this to understand terrorist activity. So these are point patterns of terrorist attacks that have occurred from about the year 2000 to 2012 in a couple countries, Thailand, Philippines, Indonesia, and Colombia. And you can see, just looking at clustering, you kind of see the 2 forms of clustering, right? Big concentrations of attacks, but also you tend to see the clustering where events appear to occur in more than one, in a close proximity. Okay, so we just structure this model very simply, actually. So the background process is going to be captured by splines, so penalized splines, where I set 1 degree of freedom per year. So, so this is allowing fluctuation over time of the background process. And then we're going to pull out the branching term, and just this is specifying that each event is going to have the same contribution to the likelihood of subsequent events. So each attack is going to have the same likelihood to produce future attacks. And then the decay term we represented as a 2-parameter. This is all discrete time. There's some slight differences. If this was negative binomial, shifted negative binomial with a mean and a spread term. Okay, so what we get is by estimating the parameters and specifying this way, we get something that's interpretable. And so for each country, B is the estimated probability that any event will come from the background process. And alpha is the probability that event comes from an excited term. So that an event, that the 35% of the events in Thailand were considered to be generated from self-excitation. In Philippines, it's very high. So in Philippines, the model suggests that more than half the events actually come from this repeated behavior. And there's a lot of theory in the conflict literature about why this is. You can break down and look at different terrorist groups that are acting, maybe to try to gain attention, and get additional resources, or it could be the same group that just had built up resources and carried out attacks. Yeah.
The alpha, is that like what people like to do, like copycat attacks, or if you see an event?
Yep,
you're
right,
following it,
Right. So that's one potential reason for why you're seeing, So every event here in Thailand, every event creates an expected 0.35 additional copycat events. Okay, and so this is the decay, estimated decay. So these are days for the different countries. And so you see after attack, there's kind of a high and elevated risk of a future attack. And as you start to get 10 to 20 days out, that elevated risk decreases. Estimated decrease. This is the overall intensity estimates that we had. So this is the blue line is the background process over time. The black line is the overall intensity. So you're seeing those chopping patterns due to the self-excitation term, the boost term. You can see where the Philippines, even though the background process comes up just slightly around 2009, the self-excitation seems to really take off here. Another application that we used similar ideas is in forecasting crime hotspots, and this is appealing to the pattern that we see that crime events also seem to have a self-excitation pattern to it. And so in the US, there's the National Institute of Justice, which is kind of the research arm of the justice system in the US. And they did something interesting. They wanted to, so the NIJ, instead of issuing grants to do research on things of interest to them, they decided to do some contests. And they'll pay out money to the winner instead of giving grant money. And so they had one of these contests where they took data from Portland, Oregon Police Department from March 2012 to February 2017. And this is going to be a live. This was a live prediction contest. So contestants had to submit their predictions at the end of February, and then we actually saw what crimes happened in March, and April, and May, and then you were scored, as far as your forecast, which is kind of interesting because, I guess as a contestant, you had the potential to go initiate your crime to make your model work, right? But it was, so you had spatial location, time, and category. There's 4 categories of crime that you're interested in predicting. And you had, you were evaluated forecast period 1 week, 2 weeks, up to 3 months. And what you had to submit is shape files. It's just a format for spatial data. Essentially, you're creating a partition of Portland, Oregon with a regular grid. And you had some control over the orientation of the grid, but you didn't have control over the size. And you had to use a regular grid, but you could kind of orient it however you wanted. And you were evaluated on identifying which grids were in the hotspot. Okay, so there was the hotspot was defined as a percentage of the area of Portland. So you had to identify the top 2% of Portland and say which locations, which grid cells would be in the 2% highest crime over these different periods. Okay, so it's not, so overall we're evaluated not necessarily in a Poisson loss function, but more of a Bernoulli scenario where you're just identifying 1 or 0 is the location in a hotspot, is going to be in a hotspot, yes or no. And you see there's kind of patterns because crimes get recorded by their address. So there's going to be patterns related to streets. Right? And you see those. And then there's areas where there's no houses, no streets. Maybe this is forested area or something. You shouldn't get any crimes. If we look at the different crime types, burglary, motor vehicle theft, street crime, and everything else, you can see that there's some seasonality patterns for some of them, kind of increasing trends perhaps. Burglary looks a little different than street crimes, motor vehicle theft, maybe a little bit of seasonality, but certainly an increasing trend, and so forth. So this was some interesting aspects of it. And our approach was basically to take, trying to create forecasting models. Because there's a increasing sequence via time. You don't want to just kind of independently grab observations for your training and testing partition, but you have to be a little more clever about it. So we had an initial period of time where we created features. And the features that we used were basically elements of the boost term for the self-exciting process. So we just took a grid cell and we looked at essentially when crimes occurred in that grid cell in the past and what types of crimes they were. And we did that for every grid cell, generated features from that. I'll show you the form of this in a minute. We fit a model that was a binary regression model. Just trying to identify if a grid cell is going to be in a hotspot. So this is the type of information that was submitted to the contest, was a partition of Portland, and we labeled in red those cells that we thought were going to be in the highest percentage. So we created a logit of the probability that grid cell J is a hotspot for crime type M. And we model this, so this just looks like our Hawk's terms. Right? We have a background process, which is intercept for crime type M, and then we have this boost term over here. The difference is, the added complexity is that now our boost term is, we want to model how likely this grid cell is in the hotspot for crime type M, but our past events could be of different crime types. So MI was the crime type of a past event. Okay. And so we can say that maybe if a street crime occurred in a grid cell, that may increase the likelihood of a burglary crime. So, and I won't get into, there's some crime theory related to how different crime types can give indication of forecasted crime. Broken windows theory is a popular one that you may have heard of. Okay, so this is essentially kind of the format of a mutually exciting process, where you can have a multivariate point process, one for each crime type. And then we have this, using our decomposition, we have a branching term now that's also going to be 4 by 4, because we have 4 different crime types. Then we have a decay term, and then to add a little more flexibility, instead of just trying to find an exponential, here, what we're actually going to do is model it as a mixture of exponentials. Okay, so we're going to have a mixture of exponentials of various decay. And so we get something that looks like this. This is our crime type of interest, the target crime type. So if we want to model street crime, so I should say, this just becomes a estimation. So we're going to fix the decay term according to an exponential with a known and pre-specified parameter. And then this just becomes a coefficient that we can estimate with logistic regression. Right? And here I'm going to use lasso penalized logistic regression. And so I can set some of these branching terms or coefficients to 0. Okay, and these are the resulting coefficients from our penalized logistic regression. And so we have, to predict street crime, we can look at street crimes that happened. So we're looking at past street crimes using an exponential decay with a mean of 10, with a mean of 50, with a mean of 100, and so forth. So we're looking at recent crimes versus crimes that happened in the very distant past. Okay? So by using a very small term here, this indicates that our exponential decay is very flat. And so we're essentially just, this term is capturing essentially something like the overall number of crimes that have occurred in that grid cell anywhere within the training And then anything that's important here for small values and very recent crimes are important. Okay, so we say to predict street crimes, past street crimes are important. These have the highest coefficients, but also motor vehicle thefts have some influence, and even burglaries tend to have some influence as well. And then we see things similarly for burglary crimes. Of course, there's not very much short-term impact. So if there's this also has some interesting criminological theory. But if your property is prone to a burglary crime in the past, it probably still is today, unless there's been some change in the environment. And so besides, I think it was mentioned that I can look at my route into places based on crime. I'm also very interested in looking at the neighborhood of locations, right? And looking at things like, is there a gate to enter or not? Is it easily accessible? Is there some sort of guardian or supervision? But anyway, it turns out that burglary kind of has this interesting property that there's not a lot of recent influence on it. Okay, this is just the overall H function, RDK. You can see that the boost is a function for burglary crimes. Past burglaries have an effect. It has a slight decay over time. So this is our time in days. So this is about 1 year. So you can see that you get a burglary crime. There is maybe an elevated risk, but it stays pretty constant over time. Where for street crimes, there actually is a pretty sharp decay. So for street crimes, the dynamics of that are going to be such that whoever does holdups on the streets tends to move around. Okay. Okay, the last thing that I want to get to is modeling social influence. And we actually have some papers on fake news dissemination, but here I'm just going to look at influence on Yelp reviews. And so I showed you this example of in Las Vegas, there's a restaurant called Mount Everest India's Cuisine, and people, you get on and you say this is a 4-star rating, and you can give some text description of why you gave it a 4-star rating. Right? Now, if you're a business, this is something that that I've looked at for Amazon as well. Amazon, of course, people make reviews on it. And Amazon wants to understand the quality of the product. And so these reviews can be helpful for that, obviously, right? But sometimes before you visit the restaurant, or even if you decide to make a review, you might look at past reviews, meaning that you can introduce a bias in what you're going to report, right? So this review may influence you to give a certain star rating. And so this is happening. This is common. People want to do similar things to what others do, so you want to fit in, right? But then there's some people that always want to do the extremes. But the important thing, if I'm Mount Everest Cuisine and I want to use this information to help me understand my business, I want to kind of eliminate biased opinions. So I want to remove reviews that are either fake, or also reviews that were kind of influenced by a previous review. And I just want to get the raw, unbiased estimate of my restaurant. Yeah.
So this example, that's based on like powerful children of the immigrant.
Exactly. That's exactly it. Yep. So we just want to estimate the background term and remove the children. So that term for this is stochastic declustering in the earthquake. Right, and so specifically, so this is just, this is what you saw before, 5-star reviews, and here I'm doing a non-parametric estimation of the average star rating. So the average star rating, this always gets me upset as well. When you see the star rating, you just see the number. I want to know what it is now, not what it's been over the last 10 years, right? And you can see this kind of looks like it dips, it comes back up, and what I want to focus on is this dip here. And you can see this corresponds to this large number of 1-star reviews. And so if I'm the restaurant here and I see this dip, I want to know, okay, do I need to really change something or not? Is this just my competitor trying to inject bad reviews in my business? Okay. So if we look, so here's an example. At day 1681, there was a 1-star review, and you might not be able to see this very well. Let me try to read it. So this review says the worst part is the staff at this restaurant. They don't know how to interact nor take care of their guests. Okay, so there's an explicit statement about service is bad, right? They don't know how to take care of their. Well, the next day, right? The next day, 1 day later, 5-star review, and in highlighted in blue, the owner and his son were wonderful hosts. We were greeted with a smile and seated right away. It's almost like a direct response to this negative review, specifically on service. Okay, next day, the owner was really friendly. Again, it's kind of unusual that you would just put these kind of comments in, right? And maybe they were influenced by this review. And then we have one that doesn't seem to really have any connection to our bad review. But then 2 days later, we have one. It shows they care. Please visit and enjoy. Right? So maybe this is a close friend of the owners of the restaurant, right? It's specifically very nice. Come in. So essentially, what I'm pointing at is that we want to maybe downweight these reviews that are almost not a real reflection of the quality of the restaurant, but they're really just a response to what you're saying. Right, and as we said, the big idea here is just we just want to use the back. We want to estimate both terms, but essentially remove the components that are influenced or potentially biased, and just concentrate on the background rate. And so we have a similar setup to what we looked at before, where we have a branching ratio that's a function of if we want to predict the intensity for a 5-star review, and does 1-star reviews tend to increase 5-star reviews or vice versa. So we have a 5 by 5 set of branching terms and potentially 5 by 5 set of decay terms, and allow those to differ as well. And I'm not going to go into the details of how you estimate everything. This one had a fair number of estimated parameters. But what we really want to get at is kind of this expected unbiased star rating at time t is just going to equal a function of the background terms, right? So eliminate the exciting terms. Okay, so yeah, around 80 parameters, and I always use penalized approaches primarily. So again, try to use L1 penalty to force some of these coefficients to 0, and also did some other shrinkage to try to encourage the coefficients across star ratings have similar values and so forth. And we get something like this. This is for this Mount India restaurant. And you can see that overall, this is the intensity of 2-star ratings. All the ratings tend to go up, mostly over time. We see this big boost of 1-star ratings down here, but we've been able to kind of eliminate those by using the flexible background process here. And so these are going to be attributed, all those 1-star reviews are going to be attributed to the self-exciting or the mutually exciting process, and can kind of be eliminated for estimating the star rating. Now what I have over here are some, the way that we can interpret these parameters. So the branching ratio here, this is saying if the, let's see, M was a previous star rating. So if we had a 1-star review, a 1-star review is estimated to produce an additional 0.37 1-star reviews. Okay, so if someone makes a bad review, there's actually some encouragement for other people to make bad reviews. Right? It's okay to criticize the restaurant that way. We have something also interesting, is a 1-star review actually leads to an expected 1.1 5-star reviews. So either this is just Yelp self-correcting, so people that are saying, oh no, that's really not 1-star, we love this place, or maybe it's the ownership getting involved in the star rating as well. Right? It's kind of interesting pattern. And this term, this pi, is just the proportions. So this is saying of the 5-star reviews, about 5% of the 5-star reviews can be attributed to previous 1-star reviews, and about 18% of 5-star reviews can be attributed to past 5-star reviews. Okay, so you kind of look at these and try to understand these estimated parameters, to understand the characteristics of the restaurant. And when we estimate the star rating with just the background process, we see this dip. It's kind of attributed. This goes away, and it looks like maybe the restaurant didn't have a very serious decline. So you don't want to start firing the chef or anything like this here, right? It may have been a bad response. Yeah, question.
So the previous slide, do those, like, I guess causal kind of review, is that for an exact previous review, or the one immediately before that 5-star review?
No, it doesn't necessarily have to be the one prior to it. I mean, this is a good question because we're looking at so when we, this is Yelp. They actually provided the data. Yelp releases some of their data over time. We did have the sequential order of when the reviews were made. What we don't actually have is the order that you see it when you log into Yelp, and so that's a bit of a limitation because they don't necessarily put the reviews in order, temporally order, but they kind of have their own algorithm to determine what's going to be the most valuable review. And so there's a little bit of a limitation, but no, these, this 1-star review could have been 10 reviews ago, potentially.
Is alpha then, like alpha 1.5 is the expectation after time t in perpetuity, like it will generate one
Yes.
monster, it will
Yes,
generate
sometime in the future.
one more.
I'm not showing the decay terms. You can kind of see it here. It's a very sharp decay. So an event occurred, a star rating, review's made, and then it's just a matter of a few days before that decay wears away. And I think that makes sense, right? You're showing the review, and that's if you don't see the review, it can't influence you. So it makes sense to have that sharp estimated decay. Okay. Yeah, the last thing I'll just point at is being able to estimate the kind of this causal sense. What's the probability that a review was influenced? Here, it just becomes very simple expressions of the estimated parameters. Something that's kind of useful here to identify influential reviewers. We can get a value for estimating the expected number of reviews that were influenced by a particular by a previous review, right? And if we look at this over the whole system, what becomes interesting, this is something that we're working on with the fake news spread, is can we identify the influencers, right? So we can look at expressions like this after we estimate parameters and say, okay, every time this person makes a review, there's a lot of response in the system, right? And that would be an estimation or identification of very influential people. If you're thinking about that for the spread of fake news, you want to find those nodes or bots or those accounts that are actually propagating very influentially that fake news. And so these models can be used for this. Yeah, I just repeated the process over a whole set of businesses and saw some similar patterns to what I showed you for the Mount Everest India cuisine. And I think I'll just not really try to go through there, but yeah, right. So there's a lot. I mean, what I showed you is actually very simplistic. So in more interesting applications, including other covariates to account for the either the decay rate or the branching term, using text similarity, looking at the content of the text itself is going to be very useful to identify if that's a fake review or not, and so forth. Okay, I think that's what I have. I'll stop there.
Yeah.
So, you mentioned that there competitors might be also influencing rating, right?
Right.
So, do you look at it as if this restaurant is standalone, there's nobody around, or do you consider the fact that there might be?
Yeah, no, that's a great idea. So, especially trying to look at what's happening in the review process of competitors and spatially, try to identify if that's a competitor. That's a wonderful idea. I haven't looked into it. Yeah.
And that's why they might protect the rating.
Yeah.
That would be standalone.
I don't know. Maybe your student expectation is based on what they've seen before your class.
I
Right?
see only 5 through 1.
Yeah.
Nothing.
Right. It's true. Yeah, I mean, there's, I modeled this as, that this is also looking at the capturing the propensity to even make reviews. And to your point, why bother going through the hassle of logging in if you're not either really happy or really upset? Yeah.
For your tourism example, did you look into the amount of media coverage that was given to the attack?
No, we didn't look at media coverage. We did account for the attributes of the attack. So the type of attack, what group claimed responsibility or groups claimed responsibility, the size, the weapon, the number of people injured or killed. We incorporated that, but not necessarily the news coverage. But yeah, that's a great idea because that's essentially measuring how much that attack was exposed to either give the copycat effect or competitor. Yeah, a great point. But no,
Yeah, can you talk about to what extent you might model uncertainty with the events, especially in something like a neural process with Monte Carlo dropout?
Yeah, meaning the uncertainty that the event occurred or not.
Time to event prediction. Yeah.
Time to event. Yeah. So this is right. So if you're familiar with time to event or survival modeling, the intensity function is the hazard function. Right. And so, so if you look at the exponential of that integrated over time, if you don't have any other events, you can get the survival function for that. Yeah, so you can, we actually did something like this in the terrorism example to kind of look at kind of an overall probabilistic risk of another event within, specifically over time. Yeah, good point. Yeah.
I think it's already been covered in these models, so I just missed it, but can you, with this kind of, these immigrants and their offspring break away from them with some kind of rape, is there a way of having the immigrants and some of the children being kind of planted to a subgroup of the prior events? So, I don't know, you're talking not maybe about like, it's not just like, one event might spring off a ton of others, but like you get 3 in a row and then suddenly your chances of offspring dramatically go up or down.
Yeah. So yes, I've seen. I've not tried to construct a model like this, but some folks looked at it as a recurrent event analysis to try to capture the these components of the branching not only as a function of time since previous events, but also how many of those events were considered estimated to be children or not. As you can imagine, it introduces a lot of complication. Yeah, but this is actually I think a really neat idea. Because you often get, I think in a lot of kind of interesting scenarios, if you think about the propensity of you to change your mind on something, like fake news, right? It's usually something like you hear the tipping point term, right? You kind of get hit with it, and all of a sudden, bam, you switch.
I was wondering how these models kind of exhibit phase transitions, because it seems like there are some things, like anything viral in nature in some sense, you have these phase transitions, or anything like that.
Yeah, no, that's great. I'm really fascinated by this, but I haven't been able to find a sufficient way to build it yet.
Because you have to use EM so much and try to estimate like those things, but a parameter size that grows really rapidly. Yeah, it was like great, and then it's like not like viability problems, split cost processes.
Yeah, so usually there's a fair number of events, at least in the processes that we try to use for this. Like I said, I'm fairly a proponent of penalization, and so with a little bit of penalizations, usually everything's estimatable. So I guess no from that standpoint. Yeah, are you thinking about something particular one issue, I guess yes. Well, let me say this. I don't know if this is what you're heading to or not. If I modeled this as a stochastic process, then absolutely. Right? This is just an unknown constant function. But if this is stochastic, at least from the second order aspects of it, you wouldn't be able to necessarily distinguish those two terms. So from that point, yes. But it's kind of interesting. Yeah.
With the Yelp reviews, I know you mentioned there's other literature that goes into text similarity, so maybe this is getting into that, but have you ever considered using something like sentiment analysis to look at, to almost like standardize the star ratings, since those are assigned by the user themselves, and see if maybe some of this response is not actually in disagreement with the actual content of the review, but more just a response to the polarity? Because I feel like if you see like a 2-star review that has the same content as a 1-star review, you might be less likely to respond if it's 2 stars, and it might just be the polarity and sort of shock of seeing a 1 or 5-star review.
Yeah. Actually, we used exactly that concept here in this paper to use sentiment. What did we have? We had a few different features extracted from the text itself to try to look at the star rating and the sentiment and the interaction of the two, which I think is what you're getting at. Really great idea. Those actually did turn out to be important predictors. So,
If there are no more questions, it's my turn again.